So, okay. So in the last session, we started to get into some kernel optimizations, and in this session, we will dive deep into some memory optimizations. So we'll talk about coalesced access to the global memory, and also using shared memory to optimize the memory. So let's start with a code example. Let's see. Great, just checking that I'm on the right branch, which I am not. Great. So we have here this kernel that I wrote called the device memory copy. So this is a kernel that all it does is copies some data from one array to another array. And I wanted to check, is there any difference if I use different types for the actual copy? So does it matter what size of a chunk I'm copying? So this kernel, it receives some void pointers to the array. So it points to the raw data. It's not a specific type. It's a template kernel, so I get a template class and the size of the class. And what I do is I cast each array, I cast to an array of type T. And then each thread copies a single element of type T. And I want to show you the comparison in the performance if I use different elements, different classes. So I go to my test file, and I have a few different elements. So let's start with just the type integer. When I go and run the device memory copy kernel, I am doing it with 1 to the 25 bytes of data using 256 threads per block. I'm again using a warm-up phase, and then I'm recording my kernel, the device memory copy. So make run memory. So the kernel time that we get is 0.08 milliseconds.
That's for 2 to the 25 elements. 2 to the 25 integers.
So not integers, that's 2 to the 25 bytes. And each integer is essentially 4 bytes. Now let's do this for the same amount of bytes, but this time we copy in int4, which is just a struct with 4 integers.
So the amount of memory the actual memory that you're copying is exactly the same.
Yes.
You're just playing around with the types. The
Exactly.
size is the same.
Mm-hmm. Okay. So it's the exact same amount of memory, and I'm just changing the type or the amount of data that each thread is copying.
Mm-hmm.
So when I run it now, I get essentially the same time. There's a small variation depending on the actual run. So using int and int4, we get almost the same. When I use the scalar option, this is a class of 256 bits. So let's see what we get. We still get maybe a little slower, but essentially the same. Question? And now I really increase the size of each element to copy a projective point, which is much larger, at least 3 times the scalar. So now actually the time increased. So maybe can anyone guess why is that? Why would the time increase for this case?
Maybe
Because each array itself is like a sub-array of three elements. Like if you're projected
It is, but how does that explain?
I guess that the memory is divided into chunks of some sorts, and that if you go larger, for instance, a projective data type, it doesn't align with the chunk seams. So in some cases, you load from 2 chunks to 2 chunks, or something like that.
I mean, the only thing that is changing is the amount of data that each thread is copying.
Yeah, but if it needs to copy from 2 different sections and write to 2 different sections because of the seam in the middle, that's my assumption.
So yes, I think it's sort of what you're saying. The thing is that there's a limitation of the amount of data that a single thread, a limitation of amount of data that a single thread can copy in a single transaction. And once it becomes too large, then it will do multiple transactions. And then actually the data copy will become uncoalesced. And the data copy will become uncoalesced. Was? Yes. So I want to show you what I mean. Yes. So let's see.
Do we have
Go
a
back.
limitation on how much is the size per thread that it can take?
Do we have?
Like like how much data it can take per thread? Is it like, is there a limit on how much?
Yes, exactly. So a thread can take up to 16 bytes per transaction.
And this is uniform across any GPU, whatever, or it may change.
Yeah, it may change, but for most GPUs that I am using, the 3090, for example. So actually,
So then that means that like all we need to do when we copy things like this is to quantize according to what thread limit that we can get.
yes, that would be the best. I wanted to show you the Insight Compute reports for the different cases.
So actually, the time doesn't really matter. It's just the amount of work done by thread.
Yes, the amount of data that is copied. So let's zoom in here. So this kernel, this run is with the uint4 type, and I'm using this as a baseline. We can see that the memory throughput of global memory is very high. It's 880, which is close to the maximum for this GPU. And we also see L1 hit rate is 0. This, you will see why I'm pointing this out soon. And this is completely coalesced. What does it mean that it's coalesced? That with a single, this is a single read command, and now thread 0 copies, let's say, yes, in this case, thread 0 copies 4 bytes, and then thread 1 copies the next 4 bytes, and thread 2 copies the next 4 bytes. So each thread copies the next part in the memory. That's why it can be brought with a single transaction and distributed to the threads. We will have a problem once the thread goes above the 16-byte limit, because then it crosses the boundary. So if thread 0 needs the first 16 bytes and the second 16 bytes, so we will actually have a pattern that is not sequential, because for the first read, thread 0 needs the first 16 bytes, but then the next thread needs to jump over 16 bytes and take the next 16, and so on. And when the element is even larger, these jumps become larger. So for int, we're still fully coalesced. This is the report for the uint, the uint 4. Sorry, not the unit. This is the report for the int 4, or 4 ints. We still have a high memory throughput. Now, when we go to the report for the scalars, which is essentially 32 bytes per thread, we see that the throughput is still high, but now we have this L1 hit rate. So in this case, we are not coalesced because we are past the 16-byte limit, but we have the L1 cache that can compensate for this partially uncoalesced pattern. So we can see that we have, yes, we get this warning of uncoalesced, but the cache helps us compensate. But once we get to the really large elements, our memory throughput drops dramatically from 800 to 600. The L1 hits is even higher, but it's not enough to completely compensate for the uncoalesced, for the non-coalescing. I also wanted to show you the actual source, the PTX code or the SAS code. So this is the int version. Sorry, this is the uint version. You see that each thread is using this load 128. So load 128 bits. Or this is what it is using. And for the int, it's using a different command, just the simple load for the integer, because integers is only 32 bits. When we look at the field element, the scalar, you see that now we use two load commands and two store commands of 128, which adds up to 256. And when we go to the projective point, we see much more. So these commands, because we have many commands, this becomes really non-coalesced. And we see the effect in performance. So what we can learn from this is when working with points, it's best not, if we're memory bound, it's best not to load them at once, but to load them in parts. That's an optimization that can be done. By the way, in our current code, we are loading complete points, and we are suffering from this problem, but it's we don't care about it essentially because we do this in the MSM where we are compute bound. so it doesn't really affect us that much. Okay, any questions about this example?
Like if you go to bigger and bigger fields, it's still going to be the same. So you have to load smaller and smaller parts so that it can accommodate for the like 381 bits.
Yes.
There are other ways to get around it that we tried once, for example, to actually take the big numbers and then actually hold them in the memory in chunks. So we don't have them like written in the memory sequentially, but we write them. We also like how would you?
Yes. So actually, you divide them into smaller chunks and you load them
And then you
in
can load
parts.
them coalesce. But
Yes.
it does require you to sort of start thinking about it. Like you store it in a bit of a weird way so that you can access it.
So like when you say chunks, you actually mean like the size of the array, or like you actually talking about the big decomposition?
The actual element.
Elements.
If you have an element of 32 bytes,
Yeah.
you can split each element into two
Okay.
and have all the low parts
Okay. That's 16.
sequential and all the high parts sequential.
Okay.
And then you can load and store in a coalesced manner. Great. So I wanted to show another example. Sometimes this is really a simple copy, but sometimes you will have a more complicated pattern of accessing global memory. For example, with the entity. So this is an example for a segmented memory copy. What this does is I can change the amount of elements that are copied sequentially. So I copy, for example, 0 to 8, and then I go to 128 to 136. So I want to check what's the length of the data that needs to be coalesced, because not all the time you can coalesce the entire reads and writes. So in this kernel, we get the input and output pointers, the size, and I can control the read segment length and the number of write segments. I won't go into all the details. It's just some index computation and the address computation. I will show you an example. I will just print out the addresses so you can see exactly what this kernel does. So let's choose the segmented memory copy with segment size 8, for example. And when I run it, we see the thread 0 to 7, writes to addresses 0 to 7, sequential addresses, but then from 8 to 16, there are another 8 sequential somewhere else, and so on. So every 8 write to another area of the memory. So let's see. So if we start, in this case, I'm going to use the integer type. Let's just get rid of the prints. Yes. So now I start with a 32 length segment, and we get 0.87, which is almost the timing that we got for just the sequential copy. So this is actually coalesced enough. 32, if you take every time 32 sequential elements. Now when we decrease this number, we see that 16 is okay. 8 is also okay. But once we get to 4, I think this is when we'll start seeing problems. Actually, no, I wasn't changing the correct kernel. I was changing the warm-up kernel instead of the actual one that I'm measuring. So 16, a small increase, 8, another increase, and then 4 will actually, yes, we already see a larger increase when we go down to only 2 elements. Yes, so this is really bad. It's almost 2x.
So the index like 4 bytes, and now because it was in a segment of 2, it's really
Because now only every pair of threads is coalesced. But as a rule of thumb, you want to, it's best to have a total of 128 bytes coalesced. But also 32 bytes, most of the cases will be good enough. At least from the experiments that I did with this GPU of GTX 3090. But you see that this could be a major problem if you're working uncoalesced. So, yes, and just to sum up this section, I want to give you a small riddle. If you look at these two kernels, we have this kernel, each thread reads multiple elements and writes multiple elements. You see in both of them we have a loop. So I wanted to ask you, essentially all this part is the same, only the loop is different. So I wanted to ask you which kernel will give better results just by looking at the code.
The bottom one.
So you're saying the bottom one. Why?
To the indexing that the top thread would need to jump around memory because the segment length is multiplied by I, which is varying. While in the bottom one, the number of elements per thread is multiplied by the thread ID, which is constant. So the jumps would be of 1.
Okay. Anyone else, or does someone have a different opinion? Maybe from the Zoom call?
Yeah, top one, of course.
Which one?
Top one.
Yes, the
Because,
top one. Why is that?
Index is, well, TID is not multiplied by anything. So it's just, well, the memory is accessed sequentially per each thread. I mean, well, you know what I mean.
Mm-hmm. Yes, thank you. So, yes, this could be confusing sometimes, but the actual index that we want to look at is the thread idx.x. This is the one that we want to be sequential for coalescing. In the second kernel, we have the same thread that accesses sequential data. So it means that when you go over different threads, the actual access pattern would be strided. So when you want to look at the code and
You need
see,
to optimize, like, not on the thread level, but on the threads as a group.
yes, exactly. So the thing you are looking for is if the sequential index should be the thread idx.x index, which is the case with the top kernel. And indeed, if we look at the performance, this is the performance of the first kernel. What happened here? this is what happens here. You get this. And for the second one, we get a much larger time.
6.
Mhm.
Factor of 5.
No, a factor of 2, around a factor of 2.
Oh, nothing.
Okay, back to our presentation. Where has the presentation gone? Okay. So to sum up the coalescing topic, from all the examples, we saw that we need to, for coalescing, we need to use maximum 16 bytes per thread. And the best way to do it is by using int4 or uint4. Major uncoalescing can have a substantial negative effect, but minor uncoalescing can be compensated by the cache. So that is important to note.
Threshold size for minor coalescing.
So you have to test, but yes, as we saw, major uncoalescing is if you read only 1 or 2 elements in a coalesced manner. Yes, minor uncoalescing is if you have one jump. If it's a completely random access pattern, then it would certainly be bad. Okay. So, moving on, I wanted to show you an example of a matrix transpose. So this is an operation that sometimes you would need to do. So in matrix transpose, you read a row and write a column, or the other way around, read a column and write a row. So what could be the problem potentially?
It's either stored by column or by row, so the memory access would be
Uncoalesced. Yes, exactly. So it would be uncoalesced either when reading or when writing. That's the problem with the transposing. I'll show you now a code that I wrote. You cannot what?
Can you read this memory of this?
They're physical.
Yes, it's physical.
I mean, you can virtually do anything.
Uh-huh. So I have here a few kernels. First, so as I showed you in the last session, when optimizing a kernel, I want first a baseline. So here I just have another simple memory copy. And this time I don't use void pointers, I just use the elements and I copy from in to out. So my baseline is this. 0.044. And now we have here a naive transpose, 2 naive transpose kernels. One of them does the transpose in the reading and the other one does it in the writing. So I assume here a matrix that is a square matrix. That's why I receive only the row length, which is also the column length. Then what I do is the row ID is the thread ID divided by the row length, and the column ID is the one that runs faster, it's the mod. And then I read sequentially by the thread ID, and I write each thread would be writing to the next row. So I'm writing the column, and then the row ID would increase every row length thread. That's how this works. And the read is just the other way around. I'm writing sequentially and reading the columns. So let's see the the performance of these kernels. So
What's the size of the matrix?
the size of the matrix, I'm using a square matrix, which is 248 by 248.
Bytes?
This time it's elements, and I'm using a field element of it's baby bear, so it's 32, right? Yeah. So it's essentially like integers. Okay. Now when I run the write kernel, you see we get about 4 times slower. But with the read kernel, you would expect we will get the same, but actually it is much faster. I'll tell you that I don't really have a good explanation why the read one is faster.
I'll tell you why, I think.
Yeah.
It's the way that the caching is done. And when you read,
Mm-hmm.
then whatever you read is cached, right? If you have cache. And then so long as you got heaps, you will take it directly from the cache. When you write, you actually need to store it in the cache. And then at some point, you need to copy it to global memory.
So in every
Like,
read,
think of it as a
yeah.
flash. So the flash, the runtime doesn't know exactly when to flash. So maybe sometimes if it would wait a little bit longer, it would flush everything, and then you'll get something that's more coalesced. But if it flashes too soon, it's going to need to flash again.
Yes.
But
Okay.
in the read, it never happens because the read, like the caching criteria works a little bit different in read. Right?
Yes, it's most probably has to do with the caching strategy, but it won't always be the case that reads are better. It depends on the dimension of the matrix, actually. So it's best to experiment with your specific case.
Well, the best is to work coalesced because then you don't have this issue.
Right. So does anyone have an idea how to perform the matrix transpose fully coalesced?
Think of the order, right? Because it's invariant to the order that you read and write the transpose. You know what? Like you can work in the sequential order when you transpose, but you can also jump. Right? You can like transpose every like 4th element and then go back, stuff like that.
Okay. I'm not. Yeah, I'm not sure how that exactly would work. Any other ideas? Maybe someone.
Can you show the code again?
The code. Yeah, sure.
Can you somehow manipulate it for? If you switch TID from the one side to be like to make it a bit more similar to the previous example, having TID constant with a varying something, so TID would be on the side with the multiplicand, but there's the constant, and the low ID would be, in this case, the row ID and the TID would be switched somehow.
Yeah. So I mean, if you put it in the input, so the output would be the other way around, and if you put it at the output, then the input would be at the other. So you can't have it both ways, essentially. So I will give you a hint. It requires a shared memory.
Oh, wait, you mean like you write, when you do the transpose, you instead of, you put it in the shared memory and then just take it back to the correct index, like you take, in order to do the transposition, you need to take the row and write it. We put all the rows one by one. As you do, you immediately also write it back to the correct index. Because the shared memory is accessed by all threads in a block.
Yes.
So you have to use the same threads that write to actually write it in the correct location.
Yes, something like that. So you are using the shared memory as a temporary memory to do the part of the transpose each time.
You could say that it's explicit caching.
Hmm.
It's basically like caching, but you control exactly how you.
Yes. So this, if you want to visualize it, then we're taking, in my example, we will have a block of 256 threads that read a 16 by 16 block. And then we read a row, which is a sequential coalesced, and write it, for example, as a row to the shared memory. But then we read the column from the shared memory and then again write it as a row, this time to the block in the other corner of the matrix. So we also take all the data from this block in this corner and move it to this corner, and also transpose the rows and the column. And in this fashion, if we do this for every block, then all the data would be transposed, but all the reads and writes will still be coalesced.
But you need to do it on multiple rows or multiple columns.
Yes.
Otherwise.
Yes, each block is in charge of each thread block is in charge of
So that's out of order, right? Because a sequential order would just go to like zigzag, like row. Row. Here you're sort of like you're saying, I'm going to do this block first, then move to this block, then move to this block.
Yes, but as long as the block size is large enough.
Large enough and small enough, right? Large enough to fit in the.
Large enough for it to be coalesced.
Yes. Small enough to fit in the shadow.
To fit in the shadow, yes.
So given a matrix, then if we identify the smallest minor that would fit in a shared memory, like if you take an element and you say this is the minor, and then you can identify sub-minors and sub-minors and so on. So that you can then take minors, like if you have an element, you put this thing and what's it called?
Okay.
You take the smallest block that's encomposed by this.
It just needs to be large enough to achieve the coalesce.
It's called minor. Like if you take element, okay, so if you give an element, you take the row and the column, and then you take like if you take the top corner of the element, and then you eliminate this one, this column. Yeah. So that block is a minor, and then you can go within this block and then also define sub-minors and so on.
I don't think that, no, that's not. Hadar, go back to your diagram. It's basically just think of this small block, okay, and like you've got like threads that basically like write it to the shared memory in one direction and then read it in the other direction. Okay. So you got like just say it's 32 on 32. You got 32 in a warp, so you got 32 threads that first of all write the rows, and then the same 32 threads then read the columns from the shared memory.
Mm-hmm. So let's see how this is written. We have a shared memory of size 16 by 16. We have our thread ID. Now we have indexes that run on the size of the shared memory block. this jumps in 16, and this runs from 0 to 15, and so on. Then we have the block indexes, and we divide and mod by the blocks per row, and we get the block, row, and column indexes. And now we write to the shared memory. So we go to the relevant block. These represent the location of the block, and then these represent the location of the element. And we read to the row and column. We write to the row and column in the shared memory, and then we switch the row and the column in the shared memory, and this is the transpose. And here we switch the block. If here it was block column, so here's block row, and block row is switched to block column. So this is the switching of the block. But you can see that this time the row ID is the thread index. So we can see we stay coalesced in the reading and in the writing to global. And now we get, well, actually, I don't think I changed it. Shared memory transpose. Yes. Now we get almost the reference time for just copying without transposing. So it works really well.
By the way, when you do, when you take a big matrix and you split it into all these like small, like little squares, right?
Mm-hmm.
If you do the transpose in place of each little square, you get a matrix that is now not exactly the transpose of the previous one, but if you remember the indexing, you can think of it as the transpose of the previous one. Right?
Yes.
Like when you work out of memory, then fine, you can reorder everything. But you can also do it in place. Which is nice.
Yes, so you can do it in place and just remember that it's off.
But the blocks are still transposed.
Yes.
Right?
Mm-hmm.
Do we do that in the entity? I think we do it in the end because I think that we had like thoughts of doing it, but then
in the entity we didn't have to transpose in the end. In the entity we just did entities over the columns instead of over the rows, and we kept it in the same state.
Right.
Okay. So if there aren't any more questions, I will go to my last example. So the last example I wanted to show you is the sum reduction, which maybe I mentioned a bit, but the task for doing sum reduction is just summing all the elements of a single vector to a single element. So this can be done multi-threaded by a few stages, and each one sums 2 elements.
Isn't it the same code you presented with the bug of the?
Yes, it's similar to the MSM reduction phase.
Okay.
With the bug that I showed in the last session. So the naive approach would be this: each thread takes 2 elements and sums it together. But you can see that this is uncoalesced. So the first improvement would be to do it coalesced. So each thread takes the first and then the half vector jump.
In place memory? Like it's the same memory row after row after row? Is that what we're meant
Right.
to do?
So it's the same memory. And it's good that you mentioned this because that means that we need to synchronize the threads before the writing. And this is possible when this is done in a shared memory and all the threads are at the same block. So Right, because if this was a large vector, and these were all reads and writes from the global memory, we would have to separate this into different kernel calls. So each kernel call would do just a single step, and the writing and reading would be to the global memory. But indeed, another optimization is to divide it into blocks, and not to have the jump for the entire vector of global memory, but to reduce each block, and then take all the results and reduce them. So with this optimization, we can save a lot of global memory accesses and perform multiple stages using the shared memory. So now each block of threads takes a chunk and reduces it to a single result. And in the last stage, they are reduced to only a single result. So this is an example of using, this is a different use of shared memory. Before we saw how we use shared memory to improve coalescing. And here we show how we can use shared memory to reduce global memory accesses. We can also further reduce now shared memory accesses by using registers. So instead of every thread reading only 2 elements, summing them up and writing them back, we can take this red circle or ellipse and do 3 additions. Take 4 elements per thread, do 3 additions and write, and skip this stage and this stage. And then you make more use of the register space, which can save you memory bandwidth. Yes. So if I summarize the 3 optimizations of the sum reduction that I showed you, then you need to use coalescing, and then you can use shared memory, and you can use registers. And this is actually a similar approach to what we do in the NTT. We also, because NTT is also memory bound, we use coalesced read and writes. We use as much as shared memory that we can to reduce global memory access, and we use as many as registers as we can. I also can refer you to there are some more optimizations that can be done for sum reduction. Some of them are relevant only if you know the parameters at compile time. But this is actually a really good document. It shows all the optimizations, including code.
You didn't draw these pictures.
No. And you can see kernel 1, kernel 2, and you can see the improvement in each stage. An extra thing that they do, they actually, the last stages, they unroll with a device function instead of using, so it saves some conditions and conditional, which improves the compilation and improves the timing. So you can see this is the total list of optimizations. Divergent branches, sequential addressing, and so on. So I recommend taking a look at this doc. Other than that, that's about it.